Now this is a 5 kilowatt system consisting of 16 panels. Here is the positive wire of one of the panels, which I have labeled it with a red tape. This is an MC4 connector, so the other wire is connected in series with the other panels on the structure. You can see they are all in series connected. Now this is the second row, and the wire goes like this in series and comes back from here. So now here I have a negative end, which is a negative female MC4 connector. So I have two connector, one positive and one negative on the structure, which will be going down towards the inverter. So here I have a PVC based plastic pipe. 1 inch is the dia of the pipe, which is going down from here safely. It's under the solar PV, so there's no chance of water entering this pipe, so it's completely safe and insulated. Here is the inverter mounted. You can pause the video and have a look at the specification of this inverter. It's a grow watt inverter, and the model number and other technical electrical specification is given. And from here we have connected that single array to this inverter to one of the MPPT, that is 16 panel connected in series. This is the DC box consisting of the DC fuse. Now only there is an output port is connected with the inverter, and you can see the positive and the label with a red tape, so that there is no chance of confusion. This is the 1000 volt 32 amps DC fuse, and the negative pole is here. This is a switch, or you can call it a DC MCB or a regulator. This is the input positive and the negative port, which will be connected later on. You can see the labeling is here, output port and input port from the DC box. So these are the input ports which will be connected from the solar panel, and here is the port for 3-phase wire, which I'm going to connect it now with the AC box. So here now two wires are coming from the solar PV panels. Positive and negative is connected with the DC fuse. Here the positive, and here the negative one just beside that. So now it's going down towards the DC surge arrestor. Here's the DC surge arrestor. Same way we have the grounding wire from the surge arrestor going towards the AC box. We'll do the common grounding for these devices. In case of extra voltage, it will be tripped so that all the other devices are safe. So it's now time to turn it on. So now the power from here is going inside the inverter. Now we'll turn on the inverter to see if it's working on solar power or not. Okay, now the inverter has started. You can see the model number of the inverter. Just now the status is red color, fault, because it is not connected with the grid. That is why it is not generating, because of the ice landing effect. What happens in this effect, when there is no power in the grid, the inverter, solar PV inverter, is not supposed to inject the power. Otherwise the extra power generated from the PV will be directly injected into the grid, and there will be the power will be flowing to the houses, residential houses nearby, and the load is not as such to support this system, so it will burn. So in order to safeguard this system, this anti-ice landing effect is there. Here's the AC box. Here's the 4-pole 32 amps MCB. You can see there is no power just because of that ice landing effect. So we'll turn it off. This is a 3-phase wire connected from the inverter, R, Y, B, and the neutral. Now we'll check the voltage, whether it is there or not. So there is no AC voltage right here. because the inverter is not injecting any AC current right now, since there is no current in the grid. Now we'll check the DC voltage. Okay. Oh, right now it's in the AC mode. Let me turn it on the DC. 1000 volt DC. Now we'll check the DC current. That time, okay. Now it's in the DC mode, so it's 613 volts in a series of 16 panels. That is 315 watt each. So the inverter is operating safely. Here is it. Now we explain with the single line diagram. From the PV panels, the power is going to the DC fuse towards the grid tie inverter, where the DC is converted into AC, and finally to the solar meter, which shows that how much AC that you have generated from the solar PV. Then it goes to a consumer distribution panel from where the load is connected, and the extra power generated from the grid goes towards the net meter and is injected into the government grid. In case the load require extra power, that comes from the bidirectional meter to the distribution panel. So the bidirectional meter shows both whatever you have imported and whatever you have exported. So the electricity bill is modified according to that. In case you are exporting more, the electricity bill will obviously go down. So this is a net metering system. That's how it works. And in case you have a doubt in this system, you can click on the link below on my blog and get the complete detail of this project as to what are the specification of single modules and whatever required to develop all these. So the yellow meter is the existing meter in this diagram, which will be used as a solar meter just to show whatever is produced from the solar PV. And the green color meter is a net meter